All right. Welcome to the other half of calculus. First half of calculus you did was differential, taking the derivative. And now we're going to talk about the antiderivative, aka the integral. So whereas before for derivatives we differentiated, now we're going to integrate. So the integral is the type of problem. Integration is the act of taking the integral, and it is also referred to as the antiderivative. All right. Welcome to the other half of calculus. In differential calculus, you learned of all the fun things that you can do with the derivative. Now you'll learn to do the reverse, how to take an integral. There's a bunch of new fun things that you can do with integrals too. So we've learned how to take the derivative. So now we're going to learn how to take the antiderivative, the integral. It's like going backwards. Remember all those derivative rules. The antiderivative, or integral, is a derivative in reverse. New notation, facts, and symbols. The antiderivative of f of x is capital F of x. So if you see a capital F of x, that is the antiderivative. Like the integral has already been taken. It represents the integral. Okay, now here's something that makes sense, but it's a little mind-blowing. Each function has more than one antiderivative. In fact, there are an infinite number of antiderivatives for a function. Think about it. What's the derivative of x squared plus 5? That would be 2x. X squared minus 7 would also be a 2x. X squared, 2x. So this was the original function, and this is the derivative. Okay, well now I'm going to go backwards. So now I'm going to give you 2x. You're going to integrate it and tell me that it's x squared plus 5. Or you're going to integrate 2x and tell me that it's x squared minus 7, or that it's just x squared. I have to give you another piece of information for you to be able to know what that constant term is, because when you take the derivative of the constant, it goes to 0. Well, I can't integrate something I don't see, that I don't physically have. So, to represent this number, we're going to represent it with a plus c. And c is going to be your constant of integration. And the big joke in calculus is, oh my gosh, did I forget to write my plus c? So if I integrate 2x dx, have to have the dx, that's going to give me x squared, and you don't know how yet, I'm going to show you the rules. It gives me x squared plus c. Like, I don't know what the original function was that gave me the 2x. I know it had to have an x squared in it, but it could have had any constant at the end of it. So I let that plus c represent any constant at the end of it. So ladies and gentlemen, on every single problem that you do today, at the end of it, you're going to write plus c. Okay? Don't forget your plus c. Okay, rules. All right, so the first one is the integral of k dx, and k is a constant. Well, the integral of k dx is going to be kx plus c. Okay, now I want to go ahead and deal with that rule. So let's go look at number 1. I have the integral of 5 dx. So that integral is going to give me 5x plus c. Now just a word about the dx. If I had the integral of 5 dy, then this would be 5y plus c. This is just telling you what variable you are taking the integral with respect to. When their x is already in the problem, it's kind of Captain Obvious, But when you don't have any variables in the problem, you can see that it's use. But that dx or dy has to be in your integral. So I always want you to think of your integral and your dx as kind of bookends, and then the function that you are integrating goes in there. Okay? So the integral of negative 8 dx is a negative 8x plus c. And I would hope that you're already starting to see, ooh, I can see how it would be really easy to focus on the rule and forget the plus c. Don't forget your plus c. All right, let's see. If I look at my second rule, so this is k, some constant, times f of x. So I can treat that constant outside. I can kick them outside and just take the integral of f of x. So if I have the integral of 3 squared of x dx, that's the same thing as 3 integral x, square root of x dx. Because it's multiplication and that 3 is a coefficient, I can pop that 3 out. And that can come in handy. All right. If I have two separate functions and I'm integrating, notice I have these nice, beautiful brackets with my dx outside the bracket. That is the same thing as the integral of f of x dx plus the integral of g of x dx. Notice since they each got their own integral, they each got their own dx. Again, bookends. Okay, so those are all like super simple rules. Here's the big one. Here's your power rule. So if I'm integrating x to the n dx, okay, so I take the power, I bring it out front, I add 1 to it, and I put it on the bottom of a fraction. Add 1 and put it on the bottom of a fraction. And then to the power that's up there, I add 1. And then don't forget your plus c. And then this is just another way to write this. Like you could put the fraction out front, or you could put it all together. Okay, so let's look at number 3. So if I'm going to integrate x to the 5th dx, okay, so that's going to be 1 over, add 1 to my power, that's a 6, times x to the, add 1 to my power, that's a 6. Don't forget the plus c. Okay, add 1, put it over 1 in the front, or put it under 1 in the front, and then add 1 to your power. Okay, so let's look at number 4. Add 1, that would make it a negative 2. So I'm going to have a negative 1/2 x to the negative 2 plus c. And I'm trying to go slow to give you guys time to process, but also please know that you can hit pause to digest this. Okay, this answer also could be written as 1 over 2x squared plus c, because negative exponents can move. All right, number 5, 7x to the 4th. The 7 is just hanging out, okay? So I'm focused on the x to the 4th. So I'm going to add 1 to my power, that's a 5. Bring it out front and put it on the bottom. So that's going to be 7/5 x to the 5th plus c. Okay, number 6, I'm going to prep him. Okay, I'm going to add 1 to my power. That would be 3/2. I'm going to bring them out front, and I'm going to put them under 1. Well, when you put a fraction under a 1, it's just going to flip it. So when I add 1 to my 1/2 and I get 3/2, when I bring that 3/2 out front and put it on the bottom, it's really going to make it a 2/3, because technically what I'm doing is that. But then I bojangles it and I get my 2/3. And then it would be x to the, not to the 2/3, but to the 3/2, because that's what 1/2 plus 1 is. And then don't forget your plus c. Okay, number 7. Add 1. So add 5 over 5. That would be 8 over 5. Bring it out front, put it under 1. 8 over 5 would become 5 over 8. X to the 8 over 5. Okay, so again, what I'm doing is 1 over 8 over 5. And that's where that's coming from. Okay, number 8, I'm going to prep him. 4 x to the negative 1/3 dx. All right, if I add 1, that would give me 2/3. Flip it, because it's going to go under 1, that would be 3 over 2. So I have 4 times 3 over 2, so that's a 6. X to the 2/3. Again, pause it if you need to. There's some good algebra in there. Added 1, gave me 3 over 2. Flipped it, gave me 2 over 3. Flipped it, gave me 3 over 2. Multiplied it by the 4, got a 6. X to the 2/3. All right, number 9. Okay, and I'm really looking at this separately. I mean, I'm not going to write this each time, but you're thinking of these separately. Okay, so I'm going to add 1 to my power. That's a 3. Bring it out front, put it on the bottom. That's going to give me a 1 x to the 3rd. Plus, okay, that's 2x to the 1st. Add 1, that'd be a 2. Bring it out, put it on the bottom. 2 over 2 is 1. And then add 1 to the power, and then don't forget your plus c. Now, super paranoid people. Well, take this right here and take the derivative. Well, that'd be 3x squared plus 2x. Voila. It's kind of like factoring and lobstering. You lobster, and then you factor. And then you could lobster, and then you could factor. Well, I can take the integral, and then I can take the derivative. And then I can take the integral, and then I can take the derivative. And it just puts you in this circle. Okay, number 10, I want to point out how these have parentheses and has the dx outside. The dx can't just go with the last term. It has to go to everything in the integral. So it's a really, really good notation that is not nice. It's a have to, okay? So you have to have those parentheses with the dx on the end. All right, so tell you what, pause me. Pause me and try 10 and 11, but do not try 12. There is no turducken for an integral. Okay, so try 10 and 11 and then bring me back in. So 1/4 x to the 4th plus 1/3 x to the 3rd minus 1/2 x squared plus c. This one's going to be 5/4 x to the 4th plus 3/1/3 x cubed minus 3x squared plus 4x plus c. Good times. All right. Like I said, for number 12, there is no turducken. So you cannot do an integral. Well, I say that. There's no rule for a turducken. So there's no outer layer, inner layer kind of thing. So you have to lobster this. You have no choice. Parentheses, so I have good notation. That's going to be 9 minus 6x squared plus x to the 4th. Parentheses all nice and tidy with my dx. And that's going to give me 9x minus, be a 3, so that's a 2, x to the 3rd, and that's a 1/5, x to the 5, plus c. Now, please know that I'm probably going to forget my c several times, so please help me if you see that I forgot my c. All right. Number 13, again, I don't have rules. There's no product rule. There's no quotient rule. There's just, like, you know all the rules now. Like, that's it. And we got to do some trig and some logs and some exponentials. But as far as polynomial goes, there's no product and there's no quotient and there's no chain. Okay? So, I have to clean. So, 2x times, oh gosh, that's cubed. Ugh. All right. I'll come over here to the side. x squared minus 6x plus 9. There's two of them. All right, so let me run with an x and run with a negative 3. There we go. All right, and then while we're over here, let's run a 2x through that. Okay, so 2x to the 4th minus 18x to the 3rd plus 54x minus 54x squared minus 54x. Okay. Now, this is terrible notation. I have to come in here and put parentheses around it with my dx. Okay, I haven't done any calculus yet. Now, let's integrate. 4 plus 1 is 5, so 2 over 5x to the 5th. 4, 18 over 4 would be 9 over 2x to the 4th. 3, 54 over 3 is 18. X to the 3rd plus 1 would be 2. 54 over 2 is 27. X squared plus c. Whew. That's a good one. I like that one. 14, like I said, there is no low D high. But I hope even if you're taking derivatives, you wouldn't low D high this guy. I'm going to clean him up. And make sure I have good notation. Okay. So, and feel free to pause me and do these as you feel okay. Do them on your own. 1/5 x to the 5th minus 3 over 2x squared minus 2/3 x cubed plus c. Okay. Again, no product rule. So I'm going to distribute. So 5x to the 1/2 minus, when you, that's a 1 for a power. When you multiply, you add your powers. 1 plus 1/2 is 3/2. Good notation. Dx. Okay, I love fractions. Here we go. If I add 1, that gives me 3/2. But then I need to flip him and pull him out front. So it's going to be 2/3 times the 5, 10/3. X to the 3/2. Okay, 3/2. Add a 2 over 2. That gives me 5/2. Flip him, that's a 2/5. There we go. Okay, take your time on those fractions and bringing it out front. Make sure you understand I'm flipping the fraction because I'm putting it under 1. Okay. All right. Oh, the trig. Okay, remember, these are derivatives. You know these. The derivative of sine is cosine. The derivative of cosine, negative sine. The derivative of tangent, secant squared. Secant is secant times tangent. Remember, it wanted its, excuse me, it wanted itself in its name. The derivative of cosecant wanted itself in its name. Starts with a c, that's why we have the negative. Cosecant, cotangent. And cotangent is a negative cosecant squared. So, now when you see these, you can go that way. But, here's the fun thing. You're not necessarily going to see negative cosecant, cotangent. You might see cosecant, cotangent. What you've got to remember is that that came from cosecant that starts with a c, and that's why he gets a negative. How about this one? What if I was just taking the integral of sine? Well, sine is the derivative of cosine, which starts with a c, so it gets a negative. So now that we're going backwards, it's not what you're taking the integral of. If it starts with a c, it's does your answer start with a c? If so, it gets a negative. So like look on the second column. See where it says the integral of sine? Integral of sine x dx equals negative cosine plus c. If your answer is a c, then it gets the negative. It doesn't have anything to do with what you're integrating. Like here, I'm integrating a c. There's no negative over there. So it's not what you're integrating, because remember, you're doing derivatives backwards. So when you go derivatives, if you start with a c, then your answer is a negative. But when you go the other way, if you're integrating, if your answer is a c, then it's going to be a negative. All right, good times. Here we go. All right, integral, sine. Integral of sine. Sine and cosine are buddies, so he's going to be cosine. Cosine starts with a c, so it's going to be negative. So negative 4 cosine. Because it starts with a c, that's why it gets the negative. Now, this is the integral of cosine, which is going to be sine. Sine and cosine are integration buddies. Okay, they're derivative buddies and they're integral buddies. Cosine is going to be sine. Sine starts with an s, so the SIGN sine does not change. Don't forget your plus c. Okay, again, I have no rules for division, so I need to rewrite this so that it's not division. So this is going to secant, it's going to turn into cosecant x dx. Watch that good notation. Cosecant. No, not cosecant. What am I doing? Cosine. Sorry. Cosine dx. I'm worried about my notation. I forgot my trick. Secant on the bottom is a cosine on the top. Cosine's integral buddy is sine. That starts with an s, so he does not get a negative. Okay, let's see. Let's rewrite this guy. Sine on the bottom is a cosecant squared on top. Okay, 3 would be 3 over 2x squared. All right, cosecant squared was the derivative of cotangent. Oh, that's one of those ones we didn't use that often. I mean, you had it, we got to just bring it back. It's been a while since we've done derivatives of good trig. So cosecant squared was the result of a cotangent derivative. So this is going to turn into a cotangent. That ends or start. My answer starts with a c, so I know it's going to change my sign to a negative. Don't forget your plus c. Let me get some water before I choke. All right. Okay, okay, I know of no derivatives that pooped out a sine squared cosecant. Like, that's not a result of anything. So, let's go into our bag of tricks and let's clean this up. So, sine squared cosecant. Well, cosecant is 1 over sine times sine squared. Well, that's just going to give me a sine. Parentheses, dx. Good notation. Form good habits now. Okay, now the integral of sine is going to be cosine. That starts with a c, so that's a negative. Minus 3x squared plus c. Oh my. All right, here we go. Let's clean. Cosine plus, all right, now that's going to give me 3 over cosine squared. Cosine squared on the bottom is a secant squared. So 3 secant squared x dx, parentheses around the whole thing, so the dx goes to the whole thing. Okay, cosine goes to sine. That starts with an s, so we're good. Secant squared is the result of a tangent. So plus 3 tangent x plus c. Good times. All right, number 6. Oh my. Okay, the cosine squared of the sine, I can handle, I can magically turn that into something, but sine of 2x? No. Sine of 2x has a different of. So I hope you're thinking double angle. So we are going to replace him with 2 sine x cosine x. That's that one double angle. If you can only remember one double angle, that's the one you need to remember. So now this is cosine squared x over 2 sine squared x cosine x, because this sine and this sine are going to give me a sine squared. The 2 kicks right there, and then I have a cosine. All right, which turns into 1/2. Remember, I'm trying to not have any trig in the denominator. So 1/2 cosine squared over sine squared is a cotangent squared. Nope, not cosine. Cosine on the bottom is a secant on the top. Don't forget your dx. Is that right? Hold on one second. Yeah. No. Oh. Okay. All right. I see. All right. Cotangent squared is not the result of any derivative. And neither is plane secant. So, and certainly cotangent squared times secant is not the result of any. So let's back up a little bit. Let's go back up here to the top and let's reduce. How about that? Now let's try. 1/2. I have a cosine, I have an unbalanced fraction. I have a cosine over sine, that's a cotangent. And then I have a sine on the bottom, sine, that's a cosecant. Ooh, and that is something. There we go. That is the result of a derivative. Okay, so now we're cooking. So I hope you guys saw, and some of you probably saw the reducing to right out of the gate. I did not. But when I got my answer, I knew that it wasn't the result of any derivative, so I knew I couldn't integrate it. Cotangent, cosecant, that's cosecant, right? 1/2, it starts with a C, so it's going to be negative. There we go. Because the derivative of cosecant is cosecant cotangent negative. Yep. Secant tangent, that's 1. Secant tangent is secant plus 5x plus c. Ooh, love that one. Okay, so there's your trig. Well, most of it anyway. Like, I haven't taught you how to integrate like a plane tangent. Because plane tangent is not the result of a derivative. Like, so you don't know how to integrate all 6 trig functions yet. You know how to integrate all 6 results of trig derivatives. Y'all see what I'm saying? Like, you don't know how to integrate tangent, you don't know how to integrate cotangent of x, because those aren't the results of a direct derivative. That's coming, but not today. Okay. What if we had more information and could actually find the c? Write the equation of y where dy dx equals 3x plus 5 and y equals 6 when x equals 0. Okay, hold the phone. What is this? That is a derivative. Well, what is a derivative doing here? We're integrating stuff. Well, guys, if that's a derivative and I want plain y, like it's all, here was y, and I took the derivative of it and I got dy dx. Well, I want to get back to y, so I want to go the other direction. So I'm going to integrate dy dx, And that's going to give me back my original function. Ladies and gentlemen, I present to you the fundamental theorem of calculus. If you integrate a derivative, they cancel each other out and give you the original function. So I need to integrate 3x plus 5 dx. Good notation. Integral, parentheses, dx. Use your rules. 3 over 2x squared, plus 5x plus c. That is my original function. But they give me enough information to be able to find c. So this is y equals 3 over 2x squared plus 5x plus c. This is my original function. I have made it back across the pond. But now I'm going to take these two numbers and plug them in and solve for c. So y is 6, x is 0. So what does c equal? Well, 0 wipes all that out. C is 6. So now, voila. That is the exact y equals. Not a generic. That is the exact one because it gave me that extra piece of information, that extra data. I can use that to plug it in and find my c. Okay. Find f of x when f prime, derivative, equals sine minus cosine and f of pi equals 3. Okay, there's the derivative. I want the original function. So I'm going to integrate the derivative, good notation. Let's see, sine would be a cosine. That's a c, so that's a negative. Minus sine plus c, y equals. F of pi equals 3. That means x is pi and y is 3. 3 equals negative cosine of pi minus sine of pi plus c. All right, pi. Pi's over here. Negative 1, 0. Cosine of pi would be a negative 1, but it's negative, so that's a positive 1. Sine of pi is going to be a 0. Subtract the 1 over, c equals 2. Negative cosine x minus sine plus 2. Shazam. Beautiful, beautiful, beautiful. These are fantastic multiple choice questions. Fantastic. Okay, last one. And it's a doozy. Okay. Now, this is F's and G's. Can you rewrite that as a G, please? I know y'all probably just had like inverse flashbacks where this is F and this is G and G is the inverse of F. And okay, but they're all G's, okay? So find G, the original function. Oh, if G double prime, the second derivative, equals x to the negative 3/2. Tells me that G prime of 4 equals 2 and G of 4 equals 6. So if I have the second derivative, I have to integrate twice. But I have to find my C after each integration. All right, so here I go. Integral of x to the negative 3/2 dx. Good notation. If I add 1, let's see, that'd be 2 over 2. That would be a negative 1/2. Flip it, that would be a negative 2. X to the negative 1/2 plus c. Y equals. All right, now let's plug some stuff in. Oh, and this y is the first derivative. This is the first derivative. So this is like saying G prime of x is this guy. I'm going to leave it with a y because I have to plug a 2 in. But this, I just integrated the second derivative, so it unlocked one of the derivatives. So now I'm only the first derivative. Okay, so I'm using this information. So y is 2, x is 4, 4 square rooted is a 2, move to the bottom is a 1/2, times negative 2 is negative 1, so c equals 3. So g prime of x equals negative 2x to negative 1/2 plus 3. I went right here. And I labeled him instead of y, I labeled him as g prime. All right, I need to integrate, and that should get me back to just g. Okay, if I add 1, that would be a 1/2. Flip it, that'd be a 2. So negative 4x to the 1/2 plus 3x plus c. Now that equals g of x. I'm going to let it be y just so I know where my 6 goes. So 6 equals negative 4 times 4 to the 1/2 plus 3 times 4 plus c. 4 to the 1/2 would be 2 square root of 4 plus 12 negative 8 plus 12, which is 4. So c equals 2. So I'm going back here. And this is going to be plain g. G of x equals negative 4x to the 1/2 plus 3x plus 2. That is beautiful, beautiful stuff. Love it. Rules, back to rules. So enjoy the rules, learn the rules, memorize the rules, and practice the rules.